What happens to a signal when it moves from a fast clock domain to a slow clock domain? Hello everyone. So in this series of videos, we will be talking about the synchronization of signals when they're moving from a fast clock domain to a slower clock domain. Alright. So if you have been watching this series of video, then you know what a CDC is, right? So what happens, say, when a signal moves from a very fast clock domain to a slower one? The most simplest example, a real life example, which I would love to give to you guys is if I start talking at a very high speed, right, then you might miss a few words in between, right? Something analogous happens here also. If from one domain to another domain, we are sending data at a very high rate and we are unable to sample all the data, then that's an issue, right? Because there will be data issues. So let's see how this situation is usually seen in terms of clock signals. So here you can see this is the fast clock domain, right? Say this data is transitioning between these two edges itself. This is the first case. Data transition happening within the two edges. So what happens is there's this B clock domain which is sampling here. When it samples the A data at the B clock edge passage, it's 0, right? So that will be transitioned here. And then similarly in the next B clock edge, what's the data? 0, right? But you can observe here if the A data is supposed to have been a sort of pulse, but here on one underscore dat you are unable to see the pulse at all because this A data is not getting sampled at all. That is, it is getting transitioned between the two edges of the receiving clock domain. I'll repeat, the signal is not stable within the two edges of the receiving clock domain. If the signal, any signal is not stable for between two passages or two edges of the receiving clock domain, two sampling edges of a receiving clock domain, then that will be an issue because missampling is happening here. Okay, this is the case one. Let's take case two also to make it a little more constrained. Let's say your signal is stable for two receiving edges, right? Receiving clock domain edges. So here what is happening, you were supposed to sample here at the B clock, first clock edge, and the value is 1, and that should have transition. But we know that if a data transitions too near to a sampling edge, then there might be issue of going metastable. So here you can see that that signal is getting metastable. The same is again happening in the next passage also. This is a very corner case, but this can happen, right? Again, it is sampling 1, but due to it going metastable and it is getting settled down to 0, so losing the data again, right? So some delay for data, if there is any minimal skew and if your design is too constrained and there is some process variation also, there will be this missampling happening or data loss is happening. So that is why this is the issue. So I think you have understood what's the issue, right? The issue is the signal from the transmitting domain, if it is not stable for at least two receiving clock edges, then there might be a chance of missampling or data loss. Now think about how to solve this, right? So then we'll be talking about the three edge rule. If I think most of you have heard this, but I'll just reiterate it. What is the three edge rule? It is a very intuitive solutions to the problems mentioned in the previous page, right? When is the issue coming? If the data coming from the sending domain is not stable, is not getting sampled in the receiving clock domain, that's the issue, right? So what can we do? Just make the data more stable so that at least once it will get sampled in the receiving clock domain. How can you do that? That is the 3S problem. It's a very simple, very intuitive solution to the problem. That is, just keep the data stable enough when you're sending it from the transmitting domain. Just keep it stable enough for at least three edges of the receiving clock domain. Got it? Or 1.5x the frequency of the receiving clock domain. If it is stable for at least three edges of the receiving clock domain, then at least it will get sampled once. Here you can see the ADAT signal, right? Just concentrate out here. ADAT is stable for three clock edges. So because it is stable for three clock edges, see here, let's say it goes metastable. It is a possibility. It is going metastable. But because it is stable at the second edge also, it will get sampled out here. And the BQ1 data will be received and then it will be synchronized. This is two deep synchronizer, so it will get synchronized and data loss is handled, right? So yeah, moving on. This is the three edge rule. So we should talk about the drawbacks, right? First drawback is this is usually called a open loop solution. So in the interviews, you may be asked what is an open loop solution for this problem. So this 3H solution is called an open loop solution. This solution's drawbacks are basically key. You might have given this solution, but there might be a change in the architecture, there might be a change in the design requirements, right? If there is a change in the design requirements, how will the other engineer know? He might know, he might not, he might miss it, right? In EC, there is no scope for errors. So this is a very general purpose solution and it might need reiterations of solutions because there might be a constraint key. Your data cannot be stable for three edges of the receiving clock domain. So during those conditions, you can't forcefully make a signal to be stable. So that is one case, or it might be as simple as you have given a solution, but design requirements have changed. The receiving clock domain frequency has increased again. So just because if the frequency increases, you can't keep on changing the design to meet that parameter, right? So this is not a one-stop solution to everything. So that is why one of the drawbacks. And the second is verifying it, right? You just can't say that, it will be stable. You need to write assertions and ensure that it is stable for three edges. And if you change if there is change in the design requirement, you need to rewrite the assumptions. If you miss an assertion, then it is an issue. This issue usually before, I think most of us haven't experienced it, but before during engineering days or even in some companies, right, they used to manually keep the oscilloscope on the design and check whether from the transmitting domain you have received that signal in the receiving clock domain. So yeah, that activity, if you guys have that set up or you could get it in your college, you could try it out. So that is also a good practice, right? So writing assertions become an issue. So this is what is called an open loop solution. And just go through it once, and I feel ki it is a very intuitive solution to our problem. Okay. Yes. Let's moving on. So now let's talk about handshake. First, I'll explain to you about a general case scenario. You call someone, you say hi, you wait for the other person to say hi, and then you talk, right? You need a confirmation key he's hearing. You just don't call the guy and say, and you start talking. He might do it in real life, but I'm just giving an analogy. Key, you say hi first, they say hi back, and then you transmit the data, whatever you want to say. That's the route, right? So here you can see a closed loop is being formed. You give something, you receive a reply to that, and then you transmit a data. So this is called a handshake, a closed loop solution. So basically, the idea is if you send a synchronized control signal and you get the synchronized signal back, after that you send the data. Got it? Just try to go explain it to you using a simple diagram out here. Okay. So this AQ1, right? A data 1 is the data to be transmitted. Let me get the marker. Yeah. This A data 1, right, is a data to be transmitted. So you are registering it, you are pushing it to the domain. This is the launch flop, this is the capture flop, and you have a synchronizer setup. Once you send the data, right, it will get synchronized. This synchronized data is sent back to the transmitting domain. So this data is sent back to the transmitting domain, and that again is synchronized. And once this synchronize is sent to some logic here, there will be some logic, right? This will process this AQ2 data and know that the A data 1 has reached this domain and send the next data packet. I hope you got it. I'll just reiterate once again so that it's more clear to you. Basically, you have to send A data. So last video we have learned that it is better to register it, right? To avoid the combinational settling, you'll register it here, A data 1, and you will transmit it. We know that we need to have a synchronization if we are transmitting it to an asynchronous domain. You synchronize it. This is the B clock domain. After synchronizing this will be the BQ2 data. This data will be processed further in the logic out here. There will be some logic, but it will also send a signal back to the transmitting clock domain. This signal will go, it will get synchronized again, and this will go into a logic out here in the transmitting domain. Once this signal reaches, then this logic knows that I need to send the next data packet. So this is solving your issue, right? So that's the whole idea, handshaking idea. Key, there you send a control signal. Once you receive it back, then you send the other data so that there is no loss of data. Okay, you could just go through the waveform here. A data, we are sending it. Then this is the register version. 1 core clock delay will come, and then again you'll send it, right? And it is getting synchronized. That's it. So here, just think about what might be the issue out here. What issue can we face here? Just keep it in mind. We'll come to that again. But yeah, talking about multi-bit signals. If you are a designer, then you know about the huge issues, the headache which comes with multi-bit signals. So basically, what is the assumption we have? So if you are a computer science student or if you have done some idea about coding, right? You'll expect if I send a multi-bit signal, a vector, indice, right? Let's say 3 down to 0, a signal. You expect that if you are sending it at the same time, you'll receive it at the same time, right? But that is not what happens in the physical chips. So you send the data, the indices are sent together. Here you can see it is sent together. But the sampling, right, in this diagram you can see the sampling might be a little different. You're sending 1, 1, 1, 1, right? But because there is a skew out here, you can observe this two positive and negative skews. Because of this skew, the signal you receive might be a little different. We are receiving here 1011. We transmitted 1111, but we are getting 1011. There is this data being transmitted wrongly. Data is not being transmitted wrongly, it is being sampled wrongly. So this is the issue. This skew of the indices of the signal causes this issue. So you might say yeah, there might be a perfect trace length, right? That is the wire, everything, all the resistance, capacitance, everything is same. But still, right, you can never guarantee that. There will always be some small rise time, fall time variations. There will be process variations, right? The chip is never uniform. If you have read the flow, right, you know key, the process will always have some variations. So it's unavoidable basically. So this is bound to happen one time or the other. So how do you resolve this? To resolve this, there are three main solutions. One is multi-bit consolidation, the second is multi-cycle path formulations, and the third one is gray coding. So we'll be going through one each of these. Just stay tuned. We'll talk about multi-bit consolidation next and move forward. Hope you got it. And if you have any queries or you're not understanding anything, please feel open to put it in the comments. I'll try and reply to you. Okay, and if you have any suggestions for the videos, please drop it down. Thank you. We'll be discussing about multi-bit consolidation next.